Hello, welcome back again to the channel. On this video we're going to discuss problem number 2 from Baby Rudin Principle of Analysis. So we would like to prove that there is no rational number whose square is 12. Before we start discussing this problem, it is a good idea if you try the problem by yourself first. So please pause the video for a moment and give it a try. Okay, let's get started. So as usual, probably you have seen the argument of there is no rational number such that its square is equal to 2. So the argument is quite similar. We start with assuming that there is such rational number. So suppose on the contrary there is a over b in Q such that a over b squared is equal to 12. Then a squared over b squared is equal to 12. A squared equal, maybe I should write down in different way. B squared is equal to 2 squared 3. A squared over, so we divide both sides by 4, so it's going to be 2b squared is equal to 3. So by assuming there is a rational number such that its square is equal to 12, then we arrive at the conclusion, hence there is a rational number p over q in the rational number field such that p over q squared is equal to 3. Okay, and we can assume that p and q has no common factor except of 1. Assume that PQ has no common factor bigger than 1.
Is it in the treasure? It's not easy one.
Has no common factor
What is it?
greater than 1.
Okay, kill it.
Okay.
But you still good.
Why can we rewrite, why can we rename the fraction a over 2b into p over q? Remember that we don't know what a and 2b's are, right? But for certain, a over 2b is a rational number whose square is equal to 3. Okay? If there is such a rational number whose square is equal to 3, then we can write down p over q into its lowest form, which means that p and q has no common factor greater than 1. Okay, so therefore there is this number p over q such that p squared over q squared is equal to 3. Okay, so now we rewrite as follows: p squared over q squared is equal to 3. So p squared is equal to 3q squared. Let me write down as star equation. Okay, we will argue that okay, maybe we can see as follows first, that 3 is a factor of p squared. right? Because 3 times something is equal to p squared. We claim from star we must have 3, p is divisible by 3. Suppose not. So if p is not divisible by 3, then when we divide p by 3, it has a remainder. And the remainder can be either 1 or 2, right? Then p is equal to 3 times something plus 1, or p is equal to 3 times something plus 2. Okay, but then in case p is equal to 3k plus 1, if we carry out the squaring, then we get 9k squared plus 6k plus 1, which can be written as 3 times 3k squared plus 2k plus 1. What we can say about this final expression, it is of the type 3 times something plus 1, right? So therefore it cannot be a multiple of 3, because it is a multiple of 3 plus 1. And for the other case, when p is equal to 3k plus 2, we have p squared is equal to 9k squared plus 12k plus 4, which can again be written as 3 times 3k squared plus 4k plus 1 plus 1. So p squared is not a multiple of 3. It's not a multiple, which is in contradiction with equation star. Contradict star. No, which contradicts star. Therefore, p is divisible by 3. Say p is equal to 3x for some integer x. Well, we can assume that p and q are positive, so x can be a natural number. Okay, now plug in p equal 3x into star. What do we have? We have that 9x squared is equal to 3q squared. So we have, after dividing both sides by 3, we have 3x squared is equal to q squared. But this equation is closely resemble the star equation, right? We just exchange the role p and q into q and x, right? So then by using exactly the same argument as above, we conclude also that since 3 is dividing q squared, therefore 3 divides q. By the same argument, as above, q is equal to 3y for some y. But this makes us into trouble. Why is that? Because p is equal to 3x and q also is a multiple of 3. which means that now P and Q has a common factor, which is 3, which is greater than 1. So, but then three is a common factor of P and Q, and this is a contradiction. Okay, since we arrive at a contradiction, therefore the very first assumption that there is a rational number whose square is 12 is wrong. Therefore, thus there is no rational number whose square is 12. And we are done. Alright, so that's it. Thank you very much for watching. If you like the video, you can press the like button and you can subscribe. So thank you again for watching. See you again on the next video. Bye.